Can you hear me, Chris? Okay, so we're going to use this computer.
That's it.
All right. You still have Jim on that, which is fine. And he has my sound, but he's still on the Mevo, which is fine. Let me just plug
There's
in.
no, there needs to be a presentation on that.
Yeah, we're not going to be able to do that. You go with no presentation? Can she just put the presentation up there? You go live without it?
Probably.
Yeah, do that. Do that.
The only thing, I just can't highlight anything.
Well,
Well, if it'll
Right now we
show
have
down
nothing.
here.
Huh?
It'll show down here.
but it's not going to show.
Yeah, next screen.
the masses.
Yeah, that's, well, without the masses,
To the 64 people.
they have to see it.
They're not gonna though, because you're on this computer. And she can't put her PowerPoint with me being the presenter. You got a
Oh.
jump drive with that PowerPoint?
Yeah.
Take that out, give me that jump drive. Where does this go to? If I pull this, is this like everything?
So right now they can hear me through this
Through
other
my
computer.
Yeah,
All right, everybody, please just hang in there.
we are close.
We are so close.
We're a jump drive away from making this work.
That's right. We appreciate you guys hanging in there. We are jumping through hoops to make this happen.
Chris, I gotta go to webinar though to bring that up, right? Do I have to get out to get back in? How do I bring that presentation up there? Go ahead.
So we're on top.
But will that bring it onto the webinar? It will, okay.
Just a couple of more minutes. Thank you very much for hanging in there. This is called working through the situation.
It's called I Need Power. I'm almost dead.
Oh, no. Well, we can grab that power over here.
That's it. PowerPoint looks like it's coming up. Okay.
Just minimize him.
Oh. So what's up here is not what's here. And then if that's the case, I need your remote.
Now, okay. Don't worry. I can't because I got the jump drive in there. Gonna have to. Sorry. I didn't think about that. Consider and hit it. I'm gonna do questions, but
Carefully.
yeah.
Or Chris is gonna give us.
Oh
the
no, I can do questions because I don't need this facing you. You just need the volume.
We just need volume, yeah. But I don't know if I'm gonna have control in
No, you won't.
making things advance or not.
Okay.
It's gonna block the whole PowerPoint. It's not all on one. Jim's smaller. He's blocked the whole. Just not because we're not going through the Mevo unless we do it just with PowerPoint. Okay. Test, test, test.
Test, test, test. Okay. What I gotta know is,
I
just
gotta,
hang in there, everybody.
I gotta move free. You ain't gonna have that.
Right, so nothing's on the top, we're only dealing with the bottom, is that correct?
Yes. Yeah, that's just your PowerPoint.
Right, but I can't advance that.
I can. You ready?
Okay, I think so.
I think I can advance.
All right,
it.
everybody.
I can't advance it. I
This is
can't
what?
advance
This
it.
is what the audience sees.
Okay,
Chris, I can't advance.
all right, well, wait a minute.
Yeah.
Hang on, everybody.
How do I advance? Oh, here we go. I got it.
Okay. So
There we go. Finally.
we're there? All right. Wow. Everybody, if you can hear me, give us a thumbs up, let us know. Apologize for the delay. I don't know, I think Russian hackers got us, I'm not sure. But for you, what's going on? Guys that all hung in there with us, thank you very much. So what we're doing today is today's Hydronics. So again, my name is Jim DePalma. Working questions is going to be Johnny Resso, and Chris is working the board in the background. What we are doing today, this is our condensed version of our advanced 4-week class. So if after this class you want to get into even more detail, on the 27th of April, we start our advanced 4-week. We're over a 4-week period of time. We will go into more detail about what we covered today. What we're covering today, we're going to talk about differences between condensing and cast iron boilers, near boiler components, sizing circulators, which is extremely important, and also depending on how you set up your system and what appliance you use, how it's going to affect your venting, which is a big, big deal. So we're going to get moving here. So, I mean, if I click.
Nope, you got nothing.
All right, so I'm going to just not pay attention to that. All right, so the terms that we should know, the terms that we use every single day in this industry is BTU. So if you call us up and you need help in sizing a circulator, we're going to ask you how much GPM you have to move. If you don't know what that is, we're going to ask you about how many BTUs you have to move, because we can convert that into GPM. So you can see on the screen that it's a British thermal unit, and it's the amount of energy to raise 1 pound of water, 1 degree Fahrenheit. I'm sorry for laughing. We're kind of tripping all over ourselves
I
here.
have no idea what it just did.
All right. I don't know where we're at. We're buffering or something.
There you go.
Okay, there we are. GPM is gallons per minute, and delta T, very important. That's going to be the difference between our supply and return water temperatures. These are the 3 main terms that we talk about every single day in the world of hydronics. We're always going to ask you these questions if you're looking for help from us. This is what our language is going to be based on today: BTU, GPM, and delta T. All right, John, next. Okay, so when it comes to building a hydronic system, you've got your choice today between a cast iron boiler and a condensing boiler. Big difference in what each product will do for you. We've been doing cast iron forever. They're very hardy. They're going to last at least 25, 30 years. The piping is not very intricate. The venting is pretty simple. You're going to use B-vent, and we're going to be running at high temperature. Okay? We have the ability to make them more efficient today by adding outdoor reset to them, but we can't really lower that water temperature. We have to only monitor and change its actual runtime for that efficiency to go up. Then on the other hand, we have condensing boilers. So you can see it on the screen. I have it behind me here. They look different. They look like an appliance that will be, right in your living space. And in Europe, that's the way they do it. You'll notice that there's 2 vents at the top. One is to bring in air for combustion. The other is for your exhaust. How you set this particular boiler up will be a direct impact on the material that you pick for venting. And this is really, really critical. On the cast iron boiler, you're going to be high temperature. You're going to use B-vent. Everybody's comfortable with that. But then when we get to condensing, depending on how you set up your system again, your supply water temperature will dictate the material that you use for venting. Okay? All right, John, if you would mind. All right, so what we're showing you here is what the boiler manufacturers give you as an option when it comes to using a condensing boiler, and what options you have for venting material. So you can see we have PVC, CPVC, poly, butylene, and stainless. We can use stainless steel for any and all fuels. That means natural gas, propane, or oil, and it has the highest temperature rating you can see there. But then your manufacturers, and every single boiler manufacturer does this, they give you the option of PVC, CPVC, and polybutylene. And it's really going to be propylene, polypropylene. I'm sorry. I'm trying to catch up to what we were going here. And it's really dictated on your supply water temperature. So what does that mean? If I set up my system to make 180 degrees, AKA like a cast iron boiler, the vent temperature will be 20 degrees hotter. So you'll be in that 200 degree range. PVC cannot handle those temperatures. So in the world of condensing, when you use PVC, you really are not supposed to go above 140-degree flue gas temperature, even though codes will give you an extra 10 degrees. That would mean my supply water temperature coming out of my condensing boiler should be 120 degrees. So if you're providing 120 degrees, you're talking about a low temp system, you're talking a radiant system, unless you design the system with baseboard and or convectors based on low temperature. Most of the condensing boilers that are going in today are going in as combis. That means they're going to make domestic hot water. And when they do make domestic hot water, what happens? We're going to high fire to at least 170, maybe 179. And if I get to those temperatures, we're talking 190, 199, we're past the temperature for PVC. What's your other option? CPVC, and there we can go up to 194 degrees. But the bottom line is, with those two pipes, you are still building a venting system. It's not made for venting. Then we have the polypropylene, and we happen to represent Centrotherm, which I have behind me here, which this piping is made exclusively for venting. All the parts and pieces are made for venting, and it can handle up to 230 degrees. So even if I'm running a low temp system and then making high temp for domestic, or maybe I'm recapturing a pre-existing baseboard system and I can run it at low temperature, but I still have to make domestic, I'm well within the temperature ranges that that boiler will be operating at. So the polypropylene, a Centrotherm system, is very important. So you have to be aware of that, all right? Our word today is cognizant. We have to be very, very aware of how we set up our system. And we see a lot of installs on the condensing side where we see PVC put in all the time, and then we see it starting to turn colors. So I want you to think about that when you're out there today working and you see those jobs and the PVC starting to turn brown. You're using the wrong material based on your system temperature. All right, we'll go into more detail on that when we go into our 4 weeks, so sign up for that class. And you'll also see here on this slide that we're showing you on the condenser world, you're gonna have two pipes. You have to bring in outdoor air. Don't try to grab indoor air for these condensing boilers. We want clean air coming in. And a lot of times you're using some pretty high BTU. You won't have enough combustion air internally, so we need to grab it outside. I also need to vent it then to outside. A lot of times we're seeing guys go through the sidewall of the building, which is fine. We have to make sure that we've got the intake and the exhaust separate, and we're not sucking in flue gas, which was going to harm our boiler performance and actually damage some components. So the hardest part of the situation is going to be making sure we can vent properly when we do a condensing boiler. Okay, so what you see on the screen now is the NTI TRX condensing boiler. This is our boiler that we represent. So since it's our presentation, we're showing you our boiler. So what's really important now, another big difference between cast iron and condensing is that condensing boilers have built-in outdoor reset. This particular boiler here has the ability to be hooked up to the internet and run off of internet weather. And you can see they have a turn down ratio. So my 85,000 is an 11-to-1. That means I can fire as low as 9,500 BTUs, which is excellent because now I can match the actual heat loss of the building during the course of the day and during the course of the winter time. So if you're not familiar with what that means, as the outdoor temperature changes, my heat loss of the building changes. We size the boiler based on our average coldest day of the year. And if my boiler can adapt its output based on what's happening outdoors, I'm going to be the most efficient that I can. All right. So we want to take advantage of that when we're doing a condensing boiler system. So that's a big difference between cast iron and condensing. Want to go forward, please? All right. So these charts, and cast iron boilers come with these charts. Condensing boilers come with these charts. This is the spec sheet that's telling you what these boilers can do. So you can see the input rating of how low we can fire on an 85 and on a 120. The boilers that you see at 110C and 150C, those are our combis. So you can see how low they can fire up to their maximum firing rate, which is really important, especially on the combi side. I don't want to oversize based on the domestic load because I may not be able to fire low enough on the spacing load, and that would lead to short cycling. So we really want to size these boilers as tight as we can to our loads to reduce the amount of short cycling that could possibly happen. All right, you'll see heating capacity and net AHRI rating. The heating capacity you'll see on the 85 is 79,000 BTUs. All right, that means that boiler will be installed in conditioned space. Then under the net rating, you see 69,000 BTUs. That means that boiler will be installed in unconditioned space, and I should lose about 15% of the capacity of that boiler off of the jacket and off of the piping. Cast iron's got the same type of ratings, so where you place the boiler will have a direct influence on actual sizing of the boiler. We need to pay attention to that. And here we're showing you on the domestic flow rate on the combis exactly how much hot water you will get in gallons per minute, which is really important because our average incoming water temperature here in our territory is 50 degrees. So that's a very accurate GPM in order to help you size your combi side. You can see how what the gas connection side is, and you can see based on 2-inch or 3-inch venting size, how far you can run the piping. Because there will be times on the condensing boiler install side where you may have a long vent run in order to get to the side of the building. All right, so this is how you interpret this information on this sheet. So now you see here, we're showing you what another big difference between cast iron and condensing is the heat exchanger. So this is a water tube boiler. This is one continuous tube, where in the past there would be a couple of tubes connected to a manifold to make the heat exchanger. Here, NTI is the only company that makes this continuous tube. It's the largest inside diameter, so we have a much higher water content, and also we can move more water with more turbulence to keep the internal of that heat exchanger clean. So that's a really unique feature that NTI has. All right, John, please. All right, and then again, the ability to add Wi-Fi to this boiler, which is another unique feature. Cast iron to condensing. Condensing will have the weather responsive built in, but on this particular boiler, I can hook it up to Wi-Fi. That means I can have Wi-Fi weather. I can also monitor the boiler from my shop. I also have the ability, and once it's hooked up to Wi-Fi, NTI tech support can also help you out in the job. If you have a problem, they can come on and see exactly what the boiler is doing at the same time. This allows you to set up service dates with your customer. The alerts, if there's an issue with the boiler, can come to you, so you can let your customer know that there's a problem before they even know. And your tech who's dispatched to the job will know exactly what he has to do before he even gets to the job. Okay, whew, enough of that commercial. Here we are here, another big difference when it comes to our systems. All right, condensing boilers have the ability to run at the lowest water temperature coming back. So our delta T for our boiler can start at a 10, can go to a 15, 20, 25, 30, even 35, maybe even 40. All right, but on cast iron, we stay within that 20-degree range because we cannot bring really cold water back. We can, but we'll damage the boiler, so we don't do that. So our high temp systems that you play with majority of the time, and maybe those are the systems that we're going to replace cast iron with condensing, they were designed for a 20-degree delta. So when you're talking to myself, John, Rob, Rick, or Anthony, and we're talking about maybe helping you size a circulator, we want to know what type of system it is. And we'll ask you, high temp, low temp, what's the delta? So when we're running baseboard, convectors, unit heaters, indirects, as you can see here, heat exchangers, high temp, that's a 20-degree delta. We've done that forever, and it's still very consistent. So even if I replace cast iron with condensing, my system side can still stay at that 20-degree delta. All right, the most important part of today is right here on this screen. This will be talked about exclusively even when we get into the 4-week. This will be talked about exclusively on the 20th of April when we do a low temperature hydronics class, which is going to be very informative. I hope you sign up for that. It has to do with this universal hydronics formula. As you can see here, it's GPM equals BTUH divided by delta T times 500. That is the basis of hydronics. This is what we do every day here at Wales Darby. We are able to now size our pipe. We are able to size our circulator knowing this, and we can make sure that the system's going to operate very simple and easy. What's important here is where these numbers come from. So the BTU, that's basically the heat loss of the project, or it's the appliance's net output. I'm either going to get those numbers from either one, or it could be from a hydronic coil, the actual BTU output of that hydronic coil. Once I know those BTUs, now I can decide on my system delta T, which is the triangle with the T. So if I'm designing a system at a 20-degree delta T, I can plug that into the formula. If I'm going to do a low temp system, maybe a radiant system, as you can see on the screen, that would be a 10-degree delta T. Where does 500 come from? That is a fixed number that will never change. And it's basically taking the weight of 1 gallon of water, which is 8.33 pounds, over a 60-minute time frame, raising it 1 degree Fahrenheit. If you math that out, 8.33 times 60 times 1, we get 499.999. We call that 500. That is always consistent. So whatever the BTUs are, based on your delta T, we plug these numbers in, and now we get our GPM. All right, John, if you wouldn't mind, please. So how do we put this into practice? So if our load here is 100,000 BTU, and I'm doing a 20-degree delta T, I do the math inside the parenthesis first. That becomes 500 times 20. I get 10,000. I'm dividing the 100,000 by 10,000. We get 10 GPM. Okay? John, if you wouldn't mind, please. We got a lot of stuff going on here today. I wish you could see what's going on. All right, a couple of clicks here, John. So if math gets you a little funny, this is how I do it on the 20-degree side. I write down that BTU, and if I'm going to divide it by 10,000, just move the comma to the left. So at 145, you're going to see 14.5. If it was 88,000, you should be 8.8. If you see 55,000, you should see 5.5. 225,000, you should see 22.5. 10,000, you'll see 1. And that last one's important because now you can identify that 1 gallon is worth 10,000 BTUs. I got the seal of approval here, so I know I'm doing that right. All right. Next screen here, and this is important for you now. We equate GPM, all right, into now pipe size. So 3/4 copper, which you guys are using exclusively out there for your zones, right? Why are we using 3/4 copper? Because on a 20-degree delta, that 4 GPM equates to 40,000 BTUs. Why are we talking about this? We want you guys to be able to look at a piece of pipe and identify it to a BTU. So I'm looking at 3/4 copper. I know it's 40,000 BTU capacity. You know, safe capacity, by the way. That tells me it's going to be 4 GPM. 1-inch copper, which you use a lot of, 8 GPM. 1.25 inch, as you can see, 14, 1.5 inch, 22, 2-inch copper. Your common sizes, right? You can see how much capacity it can carry at that 20-degree delta. You'll notice on the chart as I start to open up the delta, go to a 30-degree delta or a 40-degree delta, how the BTU capacity now can increase. So if we're going to be creative in our designs, if we keep manipulating the delta T, we have the potential to even downsize pipe. This is how important this is. Next screen, please. So the next part of the equation when it comes to sizing circulators is we need to know pressure drop. What's the resistance through our system? Because my circulator, you can see my circulator here has got to go through the boiler, through all the different components. We got to find which one of these loops is the longest, and then when we come back, so I got to make sure I can move the proper GPM and overcome the proper resistance. Next slide, please. So unless you know every single elbow, 45, T, straight run of pipe, are there any older gate valves in the system? Are there any flow checks in the system? Are there any monoflow T's in the system? And if you know them all, you can go to a chart like this and you can figure out the exact head loss in the system. And just, I want you to be aware of, we can go back once, John.
Oh, sorry.
Sorry about that. We go back and look at monoflow T, because up here in the northern part of my territory is we do see a lot of monoflow systems. A 3/4 monoflow T is worth 70 feet of straight pipe. This is pretty substantial if we got a monoflow system. So unless we know all these parts and pieces, we have an easier way to figure out, or a scientific guesstimation to figure out our head loss. All right, next slide, please. So here we're showing you based on copper pipe, based on your GPM flow rate. Here, if I'm showing you 5 GPM, how I'll have 8 feet ahead on a piece of 3/4 pipe, and that would tell me, that's going to raise my head pretty high. I would probably go to 1 inch here, because now the head loss goes down to 2 feet of head, and so on and so forth. So as our GPM goes up, our pipe size is going to have to go up to keep our head loss within a comfortable range. So we're not putting in very, very large circulators. In our Long Island territory, they happen to do a lot of hydronic fan coils. So it's important not only that we know the BTUs to bring to that fan coil and the length of run that the piping is going to that fan coil, I need to know the pressure drop going to that fan coil, because that's included. We have to include that in figuring out our head loss. So 1 PSI of pressure drop is worth 2.31 feet ahead. So if we know what that is, so on our chart, we're showing you it's about 4.7. And if we equate that across the chart, it'll tell us I'm going to be just under 11 feet of head. So that would be added to the actual head loss of that loop. So this information is really important. When you need help with this, you're going to call us up. These are the questions we're going to ask you in order to help you out. Part of your webinar today, we gave you the TACO catalog as a download. In the back of the TACO catalog, starting on page, I believe it is 48, is all this information that I am talking about. Universal hydronics formula, head loss formula that we're going to next, CV of valves and fittings. And this is something we're going to use exclusively going forward, even on the 4-week. So how do we start putting all this together? Well, to figure out my head loss, I'm going to go looking at my longest run. So if I'm doing a zone valve system, one of these loops is the longest. So I'm going to measure that longest run. This is the only run I got to be concerned about. And since I can't tell exactly how many elbows, T's, valves, and whatever are out on this job, we're going to ask you to multiply that loop by 1.5. We're adding 50% to it. Then we're going to ask you to multiply that number by 0.04, so we're not going over 4 feet per second, which is really important so we don't create noise or have the possibility of causing erosion in the components. So the example we show you on the bottom, which is the most common loop size. Every guy who calls me up, generally when they're figuring out that loop size with me over the phone, it becomes 100 feet. And so this is important. I want you to write this down. So 100 times 1.5 times 0.04, you get 6 feet ahead. So with that, if you have it written down in front of you, here's a little question for you. What if it was a 50-foot loop? 6 feet ahead. On 100, it should now be 3 feet ahead. What if it was a 25-foot loop? I can cut that in half and I get what? 1.5 feet ahead. So if I know 100, I can cut it in half for 3. I can cut that in half for 25. And now I can add and subtract as I need. So if it was a 125-foot loop, that'd be 7.5 feet of head. If it was a 150-foot loop, it'd be 9 feet of head. If it was a 200-foot loop, it'd be 12 feet ahead. And that's what we do here every day. And this is what we want you to do out there in the field. Next slide, please.
All right, we got a good question here. I'll just back up.
Great.
So it says here, when you're counting a monoflow T, are you counting 1 or 2? Most of the time, 2 are needed for that heat circuit.
Yeah, then we have to count 2.
And they both are 70 feet.
Yeah,
So
really important. So that's a great question, something to be aware of. On monoflow systems, Dan Holohan put this out years ago, and it's been pretty consistent. Generally, you see maybe 5 convectors on a loop, and most of the time you would have 1 monoflow T. That would be on the supply side. But if we need to drive a majority of those BTUs up to that convector, you'll have two. You'll have one on the supply, one on the return, and that will add more resistance. So you have to identify whether you have one or two. Great question, thank you. So on this screen here, we're showing you a typical system. Here, this is a 3-zone system. We're going to concentrate on the longest loop, and it happens to be 150 feet. You don't even need your calculator because you know a 100-foot loop is worth 6 feet. A 50-foot loop is worth 3. That's 9 feet ahead. All right, rolling on. I'm sorry if I seem a little anxious. We're trying to catch up here because we had some issues up front. So static pressure. Now I got to figure out, I got to make sure that I have the right static pressure, that I have my expansion tank charged to the right pressure to match my system. Because when I heat water, I'm going to make that water expand. I need a place for that expansion to go. That's based on my expansion tank. We size our expansion tank really based on volume, but to make sure the pressure is right, that'll be based on system height. So another quick formula for you here is to measure, and John, I always say from the top of the boiler, or should we say from the top of the water line?
I say the bottom of the lowest point of water in the system to the highest point of water in the system.
Okay, so the lowest point, so we're going to say whatever the lowest point is on that boiler to the highest point of the system. So your typical 2-story house boiler in the basement, I'm going from that bottom water line from the boiler to the top of my system. That doesn't mean I'm going to the 2nd floor ceiling. So whatever that distance is, we're asking you to multiply that by 0.43. And then whatever that number is, add an additional 4 to it. And that's going to enable us to make sure at the top of our system that I've got a minimum of 4 PSI, which is going to help us make sure that we're never airbound at the top of the system. I know you guys have jobs out there where you're always going back, maybe on a yearly basis, and you're pulling air out of the system. And it could be that it's just not pressurized correctly, or it could be that the position of the circulator is not working to your advantage. These are things that we will go over. So your typical, 2-story house over the basement, right? If we get to say 15 feet times 0.43, you can see it's a 6.5 PSI. Plus that additional 4, 11 PSI, now it should start making sense that the expansion tank that you got from your supply house was charged for 12 PSI. That's why that combination works for you. But if you've got a taller building, in New Jersey, we have, the homes along the shore that had to get raised up an additional floor because of flooding. We go upstate New York where we have 3-story homes and they finished that 3rd floor. Now the pressure of the system would have to be changed. This is how you figure it out. Okay, next slide, please. So here, if I look at this drawing, and this is a drawing that we give out to contractors to help them lay out their system. If you look at this drawing and you see your pipe sizes, without even looking at the BTU of the boiler, I look at this and I say to myself, I see 1 inch coming out of the boiler on my supply and on my return. Hey, that's the potential of up to 90 GPM. I'm sorry, 90,000 BTUs or 9 GPM. All right, so my boiler could be an 80,000 or 90,000 BTU boiler. I got 2 zones at 3/4. I'm not going to go past that 4 GPM for comfortable, sizing here. That would be 4 GPM each. I got 80,000 going out to the zones. This is probably an 80,000 BTU system by just looking at the piping. That's how powerful this information is for you. You can see by the setup here that I have my expansion tank, and then on top of that, I've got an air separator. So we are talking about near boiler components too today. Air separator like this is the Takeo 4900. And you can see in my, well, if you can get closer, Chris, here on the camera, that in my chamber, I've got pole rings in there. And what those pole rings do is when the water comes into the chamber, the pole rings are going to take the big fat air bubbles, knock them down into tiny micro bubbles, and then that's going to vent out of the top of the system. A very unique feature on our 4900 air separator is the top. It's a cone shape. It's not straight and flat to the top. My competitors go up straight and they're flat to the top. That means their upper chamber is generally flooded. With this cone shape here, this is where we're trapping air, so our upper chamber won't be flooded. And what does that do for you here? It reduces the amount of leakers you could possibly get. I do have a shutoff built into my vent, so I don't need to put a cap on here if it starts to drip like some of my competitors. This will get the air out guaranteed because there's no need for 18 inches of pipe in front of it. There's no need. We can have a short nipple right coming off of an elbow, as we're showing you here in our picture, and that will get the air out. Use these. They're going to save you a tremendous amount of purging time. And if we're saving you time, we're saving you money.
They want to know if we offer that in ProPress.
Yeah, we do. Yes, we do. All right. And if you had a threaded version, you just have to get adapters to go onto there and then press from there. But Taco does put that together in a ProPress version. You'll see onto the right-hand side of that 4900, a combination fill valve and backflow preventer. That's our 34. I always get this number
50.
messed up. 3450? 3450. Thank you. It's a good thing Johnny's right here. 3450. So that means I can set up my system pressure. I can also have a fast fill feature where I dial to high pressure, press a button, and it's going to fill to that pressure and then cut off. I don't have to worry about watching gauges or doing the hose dance, right? When I'm purging, it's going to work right to where we want and shut off, so I won't blow off the relief valve. The backflow preventer is built in. So if I have a shut off valve on my incoming, which I believe is code, you have to do it. If I ever have to replace the cartridge side of the fill valve or even the backflow side, there's a check valve inside. I don't have to drop the system side, which is going to save you another tremendous amount of time. All right, that's a big deal for it. Can you hear me now, everybody? All right, we're back. Sorry about that. We got some interesting things happening today. So if you see on the screen, you can see Johnny Russo too.
Yeah, I'm trying to get rid of that.
Say hi, John.
Yeah, what a unique day.
It's a very
Holy
unique
cow.
day. All right, now I'm
Jim
gone.
is gone. What the heck is going on here today? There you go. You're back.
All right,
Okay,
we're back.
good.
All right,
Good.
thanks for hanging in with us today. All right, so I was just talking about the low water cutoff. You need a low water cutoff. That's going to be above the boiler. We have a 24-volt version. We also have a 120-volt version. I'm partial to the 120. That will turn off power to the whole system. The 24 volts going to kill power only to the gas valve. Then as we go further out in the system, you're going to see our circulator. Its position is pumping away from the expansion tank. That means I'm going to add positive pressure to my system. That works to your advantage in helping get the air out of the system and making sure at the top of the system we are pressurized. This is our 007E circulator, ECM. I'll give you a little more details on that as we go forward. And then on the return, you can see our 2 zone valves. Those are Taco Zone Century Zone valves. Very unique zone valve. This is a ball valve body zone valve, the highest flow rate on the market as a standard 3/4. That zone valve in a threaded or sweat version can move up to 10.3 GPM. And if you get our press version, it can move 9.5 GPM. And that's at 1 foot of head loss or 2.31 PSI. That's a big deal. All right. No other manufacturer makes a 3/4 can move that kind of GPM. So that is very important to realize. And then at the top, how am I controlling these electronics? You can see I've got my TACO relay panel. It happens to be a ZVC controller, zone valve controller. I can run my zone valves, anybody's zone valves, 2-wire, 3-wire, 4-wire, does not matter. Anybody's thermostat on the top, which could be 2-wire or 3-wire power stealing, not a problem. The lights give you diagnostics, so you can see what zone's calling. First, I can even see if there's power. Then I can see what zone's calling, and I can see if the end switch made. Here we're showing you the same type of setup, but I zoned with circulators. So now each circulator is sized not for the whole system, but for that particular loop. So the GPM and head loss per loop. And what changed here is now not a ZVC panel, it's an SR, switching relay panel, that will run all the circulators, run my thermostats, and send my end switch down to the boiler.
Next,
Next, please, yes.
trying to answer questions at the same time.
Okay. We are really working very diligently today to make this as smooth as possible. Interesting setup. And then here's a big difference between cast iron and condensing is how we pipe the system. So in a condensing boiler, you will see one loop just for the boiler, and that's at the bottom there with a circulator with the triangle pointing down. That means I'm making sure I've got my flow exclusively there for the boiler. That boiler needs a specific GPM based on how you set it up, okay? So that boiler has got its own loop, its own circulator. Then I've got my supply header, my return header, and whether I zone with pumps or zone valves, I set that up. And you'll see that we've got these closely spaced T's that connect the system to the boiler. We call this primary secondary. And technically the primary loop is where the expansion tank is. So not to confuse people, kind of what we do here, we say boiler loop, system loop. And what I have here going right now is I can have two separate delta T's, two completely different flow rates. The boiler can have a 25 or a 30 degree delta, which means the flow rate will be completely different from the system if the system is set up as a 20 degree delta. And with those closely spaced T's, so you see me putting my knuckles together, my thumbs up, that's a closely spaced T. All right, I'll have two different flow rates. The circulators don't see each other, and the boiler is basically injecting BTUs into that loop. More detail to come on this in the 4-week class.
So question was up before we talked about 90,000 BTU.
Yeah.
Were you talking net or gross input?
I was talking net. Yeah. Those pipe sizes based on GPM, net numbers, guys. Those are net numbers. Okay.
Talk about static pressure how does static pressure affect the system and matching up. They're asking about, so talk about how static really doesn't affect head is what that boils down to on that question.
Oh, all right. So yeah, so static's not going to affect the head or the resistance, but I got to make sure I got the right pressure here to match my system, because again, when I heat that water, it's going to expand. It's going to push down on this bladder, and I got to be able to accept that expansion. If not, my relief valve, which is not hooked up here because this is really just a display, would be blowing off. Not a good situation to have. Mr. and Mrs. Smith don't want hot water blowing out of the boiler throughout the day. So that's critical. So let me ask you guys a question. What if my system needs a number 15 size tank, but you don't have it? You got a number 30 on the truck. Would that cause you a problem? I'll answer it for you. The answer is no. So if I oversize the expansion tank, did it cause a problem? No. If that's all you got on the job, if that's all you got on the truck, and maybe it's an emergency repair job, you're not going to hurt anything in the system. Would I have a problem if I undersize the expansion tank? And the answer is yes. I hope that answered your question.
Yep, good.
Okay. All right, moving forward, please. All right. So here is an example of a primary secondary system where we are having different different delta T's on our system. So we're asking you here, all right, if I got a 30-degree delta T on the boiler loop, Chris, they can see you right now. It's better looking. She's much better looking than me, so that's quite okay. So if you could see that 30-degree delta on the boiler, and that boiler is 120,000 BTUs, we're going to ask you to plug that 30-degree into your hydronics formula. So 30 times 500 is 15,000. So you're going to divide that 15,000 into that 120,000. My GPM for this job will be 8. So that allows me to now size the piping. 8 GPM, that's 1-inch pipe. I'm gold. Okay? And then I would size the circulator based on 8 GPM at 8 feet of head. And I believe, John, if you hit the, we should have a curve come in. There you go. So here's a pump curve, all right, from a 0015E3. And John, if you could put the arrow to where 8 GPM is, please. So on the bottom, we would find the 8 GPM. And if we go up to the top to find 8 and go to the left, that equates to our head loss. I can set a 0015E3 at medium speed, and that would take care of my GPM and head loss on my boiler. On my system side, when we use this as a training tool, we're going to tell you that's going to be a 20-degree delta T. So there's 120,000 BTUs on the system side because each zone is 40,000 BTUs. All right. I have to then move how much GPM, because now it's a 20-degree delta. That's going to be 12 GPM. My longest loop is about 135 feet. Well, I know that 100-foot loop is 6 feet. I know a 50-foot loop is worth 3. A 25-foot loop is 1.5. This is going to be a little bit over, I think about, I don't know, 7.5. Let's see, times 1.5. Whoops. 135 times 1.5 times 0.04, 8.1. So I need to move 12 at 8.1. Again, we're going to go to our chart. John's going to show you the HEPM on the bottom.
Oh, it's 12.
I'm sorry, 12 on the bottom. And if I go up to find 8 feet of head, I'm off that chart. Can't use a 0015E3. Hit the button, please. Slowly return. And then there's our 00 chart. So if we find 12 on the bottom and we go up to where 8 is, that is going to fall right under the number 8 curve, I believe.
It is.
Right?
This won't move.
And the other number 8 curve would be a 0010. So 2 different circulators based on 2 different GPMs, 2 different head losses, 2 different delta T's. That's what's going to happen when you do a condensing boiler system. So big difference between condensing system, piping, pumping versus cast iron. We go forward, please. So this is another example that we love to pull up here. All right, this is a very common design that we see. We call it the moose antler. All right, but it's still a supply and return on the top with the closely spaced T's there in the middle, and you see the boiler loop. So one of the things we like to do here is to say, all right, tell me how many BTUs this boiler is, because we're not telling you. But you can see that we give you GPM. So I'm going to use my universal hydronics formula in reverse. So I'm going to add up all those GPM, and that should add up to 27. So if it's 27 GPM, instead of dividing by 10,000, because we're going to use a 20-degree delta here, I'm going to multiply it by 10,000. That would tell me I'm going to give you 270,000 BTUs. That's the size of my boiler. At 27 GPM, Now I can size my piping for my boiler. Use 27 GPM, I believe that's gonna be 2-inch pipe. So that boiler piping is gonna be 2-inch. That means my supply and return header has to be 2-inch. Now you can see the GPM that we're telling you here per zone, and we're gonna size a circulator per zone. So 3.5, 35,000 BTUs. I got to overcome 7 feet of head. If you wouldn't mind hitting the button, John. I'm pulling up the 0015E3 again. So if we find 3.5 on the bottom, go up to about 7.5 feet of head on the left, we're going to set that to medium speed for zone 1. Same thing for zone 2. Zone 3 is 3 GPM at 8 feet ahead, 30,000 BTUs. Again, I'm going to be on medium speed. Zone 4 is 4 GPM, 40,000 BTUs, 3 feet ahead. I could set that to low, right? Because you can see where we're going to operate there. Zone 5, 2.5 GPM, 25,000 BTUs, 6 feet ahead. Now I'm just over that low into medium. I could keep it at low if I want. What's going to happen? The delta will just open up a bit, and more than likely that would be fine. But if you want to be right on the button, you'd go to medium speed. When we go to zone 6, you can see 4.5 GPM or 45,000 BTUs 10 feet ahead, has to be medium speed. And when we go to the last zone, 6 GPM, 60,000 BTUs 9 feet ahead, that's going to be medium speed. So we used one circulator here and took advantage of the different speeds in order to size each zone pump as close to the GPM and head as possible. Now, why is that a good thing? Because that'll give us better system performance and will cut down on any possible short cycling. This 0015E3 varies its speed at low and medium. So if I set it at low, whatever GPM I'm trying to move, it will follow that. That is what, 5 feet ahead, 5 feet ahead, all the way out to 12 GPM. When we set it at medium speed, it'll follow 10 feet ahead, all the way out to 8.25 GPM. If we ever have to go to high speed, then it's going to run at full speed, and it follows an actual pump curve. We'll get into more detail on this when we are doing the advanced 4-week. When we get to the slope of the curve, then we have to, then the circulator runs at full speed. All right. And as it's changing speed, by the way, it's also changing its amp draw. Okay. If you could just back up real quick. So the other pump curves came up for the double O's because we have to size the boiler. All right, at 27 GPM, you can see we're out of the range for the 0015E3. So now we're going to be, I think, what do we say? This is like 5 feet ahead or so. We're going to be in that 0012 range for the boiler size circulator. That's how we do it, guys. It's as simple as that. All right, going forward. All right. So an expansion tank, since we had that question earlier, we got a couple of slides to talk about it. I got to make sure my air cushion or the pressure that I have the tank set to is going to equal my system pressure. And as we heat the water and it heats up, it's going to press down on that bladder, okay? And the bladder has to be able to accept that pressure so we don't blow off relief valves. It's as simple as that, okay? So one of the things that we always recommend to technically size a expansion tank, it is based on system volume, but we have a cheat sheet. So if I know I'm going to be up to 50,000 BTU system, a number 15 is good. If I'm up to 150,000 BTU system, a number 30 is good. I'm getting up to a 200,000 BTU system, that's a number 60. We make 90s, then we also get into much bigger, but it's all really based on system volume, but residentially, these numbers work for you, okay?
2 questions, Jim, and I can't type in there without making things go crazy. So one guy wants to know if this is going to be recorded and posted somewhere.
Yes.
And maybe. Because of what a disaster it was, but maybe. And then the other one is how much head loss through the 4900?
Oh, the head loss is minimal?
Yeah.
geez, I don't know if our catalog gives us an actual CV. Let me look. I will look here.
Bottom line is if he's using the 1.5 times 0.04, he's got plenty of fudge in there to make it work.
Oh, absolutely. Our spec sheet here does not give us the CV rating. And if you're not familiar with what I just said, CV rating is the amount of pressure drop through a valve or a fitting. So I guess I could consider this a fitting. It's not a high pressure drop. So we're not even showing it here. So that head loss formula that we gave you, John used the word fudge. It is a wild ass scientific guesstimation. All right, by adding that 50%, all right, because again, I'm under the assumption that we're doing a retrofit and I can't see all the piping, the valves and fittings. We're adding to that head loss. That's the fudge side of it, all right? So you would have ample amount of head loss built into it. So the 4900 is not going to cause you an issue. I hope that answered your question. Okay. Since really quick, we get into this detail on the 4-week, is in your TACO catalog, there's a chart just for PEX pipe. And it's really important that you understand that when you use PEX pipe, the feet of head through there is going to be dramatically different than copper. So it's important you have that manufacturer's chart in front of you so you can see what the pressure drop is per foot. All right, 100-foot loop of copper, we're always using that 6 foot ahead. If that was 3/4 PEX, just a little FYI, that's 11 feet ahead. So that would make a big difference in your pump size. All right, so what we're showing you on the screen is that zone valve from TACO, the Zone Sentry. And there's two very important issues with this valve, not issues, features, I should say. The CV rating, the sweat and threads, a 10.3. That's a GPM. Multiply that by 10,000, that's 103,000 BTUs that I can move through that valve. 10.3 GPM, 103,000 BTUs. That's the biggest flow rate on a 3/4 valve. Your Honeywell, which is basically the industry standard, especially around here, has got a CV rating of 3.5, their standard 3/4. That's only 35,000 BTUs. So why am I jumping up and down about this? Because if I'm trying to move 40,000 BTUs through that Honeywell, my resistance goes up in a big way, which could be a reason why you have a job that works well during the wintertime, but when we hit that extreme cold day or our design conditions, it may fall short. You may fall short by a half a GPM, and that's 5,000 BTUs. That could be substantial. So the Zone Sentry, as you can see here, sweat thread 10.3. If it was press, it's going to be a 9.5. That's 95,000 BTUs. So that's a big deal here.
Guy asked about Uponor. Does it hold true with Uponor too, with the reduced?
Yes, yes. All PEX pipe has the same outside diameter and the same inside diameter. Does not matter to manufacturer. There's a DIN standard that all those manufacturers have to follow. So the wall thickness on all of them is the same. So whether you had an Uponor chart, Zern, Mr. PEX, what have you, the head loss through them are going to be the same. All right, ECM circulators. So they've been around for a while now. We've been talking about them for quite a long time. We have a lot of them out in the field. We see good success with them. If you're not familiar with them, we're going to talk about them right now. Two different types. We have Delta P circulators, circulators that would change their resistance based on a pressure differential in the system. That's the 007E, that's the 0015E3. My favorite is the VT2218. That's the second circulator you see there from the left. That is a Delta T circulator. That will measure actual temperature differential in the system and recreate a pump curve based on actual demand. So my P pumps, which are inexpensive compared to the T, will change their speed based on pressure. We get closer to what's called our system curve. More detail on that in the 4-week. That's why when we showed you that example of zoning with circulators with the 15E3, we were able to get pretty darn close to the actual GPM in head, all right? So we're not exactly there with the P pump, but we get close, going to equal better system performance. If it was the T's, the delta T's, which I have in my system at home, it's going to measure the supply and the return temperature and figure out where it has to be based on the delta T that you program into it. All right. So as we do that, it'll actually change its performance curve based on the amount of zones opening and closing. So now, if my boiler is going to change its output based on temperature, and my circulator could change its speed based on temperature also, I have the most efficient system I can possibly install out there. All right. And that is something to take advantage of. All right. That's why we do these classes, so you guys understand where and how to use these appliances. So here's the spec sheet on the 007E, and it shows you a couple of really cool features. First off, right on the volute itself, where the nuts will go in, where you're connecting to your flange, it's called the nut grabber, and that will hold the nut in place so you don't need a third hand as you're snugging this up. Almost finger tight, believe it or not, will be tight enough. Just a couple of small little turns, and that's enough. So that's a neat feature. The light will tell you how the unit is running. If we see an orange light, that means the unit's running perfectly. If we see a white light, that is called our auto unblocking air purge. That's the sure start feature. If I get air trapped in the volute, if there's air trapped in the volute back here, that circulator is going to run at high speed. I believe it'll try this up to 100 times to burp that air out. That's a big deal because that can possibly stop a service call. And then if I see a red light, either flashing red light or a solid red light, this is our auto unblocking. This is to make sure that if we have any debris in the system that could be locking up the rotor on the circulator will try to unlock itself. It'll try that up to 100 times, and if it cannot, it'll go to a hard red light. That's a hard stop. The circulator turns itself off. So now you have an opportunity to go there, clear this blockage, and turn the circulator back on again. So a couple of really, really cool features. It's only a 2-wire circulator, no ground, because the body is a composite body. So we don't need a 3rd wire for the ground. Okay. So there's a picture of the actual cartridge of this circulator. All right, you can see the hole in the middle. So this is still a water lube circulator, just like we do with our standard 00 series. That is the permanently magnetized rotor. And then what you see, that bronze looking thing above it, that is the bio barrier. The hell's a bio barrier? If we have corrosion in the system, that is called magnetite. That is the metal non-ferrous components in the system breaking down. And since that is a permanently magnetized rotor, because it is a DC driven motor that's permanently magnetized, it's a very powerful magnet that will attract magnetite toward it. And the bio barrier stops that from coming through. We're the only kids on the street that had that built into our circulator. Our competitors with a like type of ECM circulator are now telling you, requiring you to have a mag dirt separator on the system in order for that mag dirt separator to capture that magnetite and not take out their circulators. We have it built into ours. We don't need it. If you're looking for a mag dirt separator, though, we make it in the world of Taco. It's way back here. I don't know if Chris can see that with the camera. Kind of looks like our 4900, but it's different in that it's upside down because we want to capture any of that mag dirt in it. The magnet is this half moon magnet. And when I unclip it, you can see the magnets that are on here. And because of the circular feature of the magnet, the way it goes around the chamber, we actually have a more powerful magnetic field. We can capture more of the magnetite much easier than our competitors. So a couple of really cool features that Taco has. If you need a mag dirt separator, we have them too. All right, as we go on to our next screen here, here's the difference between a pump curve between our 007E and our standard 007. Why did a 007, or why does a 007 work so well around here on our hydronic systems that have baseboard and convectors because we can move a lot of GPM with it. Those are usually larger pipes, 1 inch, 1.25 inches, 3/4, not a lot of resistance. So it's a lot of GPM that we have to be able to move. 007, nice long flat curve, can handle that. The difference in the curves is the 007E is going to hold 10 feet ahead, up to 8.25 GPM, 82,500 BTUs. And then as we go on the sloping side of the curve, that's where we will run at full speed and high amp draw. We will bounce back and forth as zones open and close on that 10 foot of head mark. And as we do that, it also reduces the amount of amp draw. So it's a variable speed circulator that you don't have to program. It will do it on its own. Okay, it'll get close to the pump curve. Doesn't match it, the T will. Okay, yes, we are flying here as best we can. So what do you see on the screen next? This is a question we do get asked when we do our classes. Why circulators or why zone valves? Which one to use? If you cross the Hudson River over there, they're big in zoning with circulators. On the island, it's circulator city. Over here, it's kind of a 50-50, maybe a 60-40 zone valve to zoning with circulators. We basically decided it this way. If my BTU of my system is a net of 130,000 and less, that would be a zone valve job. That would mean even for my smallest zone, my circulator is not so big that I will over pump or short cycle on that smallest zone. If I'm 130 and higher net, then I want to have a circulator per zone. This way I can dial in that circulator as close to the BTUs required and the head loss per zone. So here we got an example coming up, I believe. Yes. So here on this 85,000 BTU boiler system, 20-degree delta, immediately you guys should be thinking that's 8.5 GPM. Since I got 3 zone valves here, all I got to do is concentrate on that 137-foot loop. And I believe that 137-foot loop is going to be just a little bit over 8 feet ahead, 8.5 GPM, a little bit over 8 feet ahead. That's a 007, that's a 007E, that's a 0015E3 on medium speed. Okay, now if it was 175,000 BTUs, all right, 20-degree delta, that's 17.5 GPM. That was one circulator for that one zone at 62 feet. Well, that's going to be a little bit over probably 4 feet of head. That would be way too big, and I would short cycle that zone like crazy. So what we would do here is I would size a circulator per zone. Okay, we didn't give you a GPM there, but you know, just for math, if we divided that 175 by 5, it'd be 35,000 BTUs per loop. You could figure a GPM from that point, 3.5, and then do your head loss formula here. So your biggest loop at 151, it's a little bit over 9 feet of head, 3.5 GPM, little over 9 feet ahead. It's still a 007E, 0015E3, or even a 007. All right. So if it was a 17.5 GPM circulator, it would be way too big for that smallest zone. That's why we do that. Okay. So John, if you want to hit the next screen. All right. So basically here, by pulling up that chart, we showed you how to pick those circulators. Okay, going forward. So there's the little spec sheet on the 15E3. Why am I showing you this? Because right on the box, we will tell you at low speed how much foot of copper it can overcome. Head loss, 85 feet. On medium, 165. On high, 242. Our competitors don't give you that information. That's right on the box. So you will know where you're placing it, what you're actually going to be able to overcome. So that's a big plus for you. Okay. We go to the next screen. The VT2218 Delta T, my favorite, because I can actually measure the system delta T based on temperature. And if it's a zone valve system, as they open and close, I'm going to recreate a new pump curve. Next screen, please. So we're showing you here, based on GPM and head, we have to pick the circulator based on where we plot that on the pump curve. Again, more detail in the 4-week. We have to either be on the curve or below. In reality, where we plot it, the system, the circulator is going to follow its pump curve. So even though I need to move 7.5 here at 9 feet ahead, what will actually happen is I'm going to end up moving 9 GPM at a little bit over 11 feet ahead. If you hit the next screen, John. So the system curve actually works the opposite way of the pump curve. It goes from left to right instead of, I'm sorry, it goes from right to left instead of left to right. So in actuality, that single speed circulator is going to work there at about 9 GPM and about 11 feet ahead. I only need to move 7.5. So I am over pumping, but not by much. But what if we can actually match what we need? That's what we're going to show you next. So we go to the next slide here. As the zones open and close, if it was a single speed circulator, right? So at 75,000 BTUs, we're going to say it's 25,000 BTUs a zone. So if only 2 zones call, I need 50,000, right? And you can see that I'm going to over pump by moving 6.5 GPM or 65,000 BTUs. So I'm moving more BTUs than I need, and I'm starting to ride up on the high side of the curve. So my potential now of shortening my delta T is getting even greater. I go to 1 zone, I only need to move 25 GPM, 2.5 GPM, but I'm actually moving 4, and I'm really on the high end side of the curve. So now my potential to over pumping is greater. So that can lower our delta T. So the next slide here is going to show you exactly what that means. So we can take our hydronics formula and turn it into a way to figure out the delta. So if you plug in the GPM and BTUs that you're trying to move, and the number you see on the bottom for GPM is the actual number I'm moving if it was a single speed. So 1 circulator, single speed for these 3 zones, that's where the 9 comes from. And if I do that math, I'm actually producing a 16-degree delta instead of a 20. If that was now 6.5 and 50,000 BTUs, because only 2 zones called, well, actually now we squeeze the delta down to 15. Not too bad yet, but we're going into a bad spot if only 1 zone calls. So now it's 25,000 BTUs, but in actuality, I'm moving 4. That's going to end up being 12-degree delta. That's, I believe, a 30% difference. And that's where we're going to short cycle. And that's when it's the average coldest day of the year out. When it's 45, 50 degrees out, that could get down to single digits. That's no good. That's why we short cycle. And that's not efficient. That costs you money if that's your house, right? Because you're using more fuel because you're going to be going on and off, on and off. So these are the things we want to avoid. Next screen, please. So next screen shows you the install of our VT2218. What's the difference? 2 thermistors. One goes on the supply, one goes on the return, comes with the circulator. I can dial in from a 5 to a 50-degree delta here. And now the circulator, no matter what the boiler does, will always speed up and slow down to maintain whatever delta you want. So when I use that on a condensing boiler on the system side, as the boiler is going to change its output, my circulator going out to my system will change its speed, and we can get a match made in heaven to get the highest efficiency possible. All right, so the next slide will show you if that same system had the VT2218, as all zones call, it runs exactly where we have to be, 7.5 at 9. If we go down to the 2 zones, I'm moving my 5 GPM, and it happens to be a little about 6 feet ahead. And if 1 zone calls, there's my 2.5, and it looks like it's about 3 feet ahead. You can't get any better than that. If the circulator can adjust and match the curve that it needs, the efficiency can be the highest it's going to be. Next screen, please. All right, so there's the adjustability on that circulator. All right, yes, this is a premium product, but what it's going to do for this system is going to be incredible. Next slide. So it'll work within that whole green area. It'll recreate a pump curve. Now, if you get really low GPM and head, well, the lowest it's going to go is that you can see at the bottom of the curve. Okay, so there'll be times you may be down there, and that's just where it's going to be. Okay, can't go any lower. All right, plus you have the option if you want to pick 4 hard curves if you want. And maybe you want to do that if you're feeding a fan coil because you want to guarantee a specific GPM. All right. Next slide is going to show you something that's unique to take a 0018 E3. This has Bluetooth technology. If I set it to constant pressure, thinking of our basic systems here, it'll actually show me on my phone where it is performing on the pump curve. And with my finger, I can actually dial in exactly where I want it to be. Nobody else has something like that out there. Pretty cool feature, okay? And then as we start to get into our bigger 00Es, this is our 26E and our 34E, we're gonna start to replace a lot of our 00s with E system circulators. So the amount of circulators that we're gonna have available to you will drop, but we can handle more system demands. So you can see what these circulators will start to replace. Now I'm getting into replacing my 10s, my 11s, my 12s and 13s with variable speed ECM circulators. Whew. So what do you think, John? So the question was, is this recorded? Yes, they're always recorded. You can find them on the walesdarby.com website. You can also go to hvacinsiders.com
This is not me.
and find it there. It was a little wonky today because of some technology issues, so we have better ones already recorded, so you probably watch those instead. Any other questions today?
Does it set itself up automatically on install? Does it set itself up automatically on install?
The VT?
The VT, no, it comes out of the box at a 20-degree delta.
Right. You decide what it's going to be. And when that circulator is set, when it initially comes on for 30 seconds, it's going to run at high speed because it has to establish that temperature differential. Once it knows the temperature differential, then it starts to adjust its speed based on what's open in the system. Okay, great question. Thank you. Anything else there, John?
We are good.
We are good. All right, we went a little overtime today. Actually, we really almost caught up.
We did okay.
Whew.
We did okay.
We thank you for hanging in with us today. We got to figure out what those issues were. We'll fix them, we promise. Next week on the 13th of April, I hope you come and meet Rob for our heat pump water heater, A.O. Smith heat pump water heater. This is still relatively new technology that a lot of guys don't know about. You want to take advantage of this and you want to understand how to size it properly, all right, and how to install it. These are the things Rob is going to go over. What's really exciting also is the class after that. That'll be Anthony Tosley for low temp hydronics, which is something you want to tune in for because of all the different options you have out there now to build low temp systems. The industry is being pushed there. This is things you want to be aware of. And then to fill in the blanks on what we did today with more detail, John and I start the advanced 4-week, which will kick off on April 27th. And for 4 weeks from that point, we keep building as the class goes on. We'll take you into heat loss. You're going to do a lot of math. We're going to give you troubleshooting. We're asking you questions that you're going to have to answer to us. It's really a lot of fun. We enjoy it immensely. So again, thank you very much for being with us today, and we'll catch you next week. Thank you.